Hey guys. My name is Srinjoy. This is Brandon. This is our research from ISERM this summer. And we work jointly with SUMS2020, our mentor with Benjamin Hutz, and our grad mentor with Grayson Johnson. So we're going to talk about characteristic zero automorphisms in M3 and M4. I will go on to describe exactly what those words mean. Characteristic zero just means we're working over a characteristic zero field, so you can just think of the rationals. So a polynomial is an expression that all of you know. It's, and the degree of the polynomial is the highest power, but then we define a rational function. And a rational function is essentially a ratio of two polynomials. But what's important to note here is how we define the degree of a rational function. The degree of a rational function is going to be basically the maximum of the two polynomials that are making up the denominator and the numerator. Similarly, the resultant of two polynomials is a function, and all you have to essentially know is that it's zero if and only if the numerator and the denominator of the rational function share a common root. And so this motivates the definition for the RAD-D. So RAD-D is essentially going to be those rational functions whose resultant is not zero and whose degree is D. And all this basically means is that you're canceling out all the common factors. So you're left with rational functions which have no common factors between the numerator and the denominator. So now let's get into the dynamics of it. So the dynamics that we discuss is going to be kind of different from the dynamics that Mira discussed. So dynamical system is essentially a set S and a function from the set to itself, which we write as, and then we have the iterations of the function, which is basically just applying the function to itself a certain number of times. And then studying the properties of this function and all the iterates of the function essentially describe the properties of that dynamical system. So point Z is said to be periodic if at some future point, at some future iterate of that function, you return to the same point. And similarly, a point is called pre-periodic if there exists some gap before the periodicity shows up. So an easy example to see this is f of z equals z squared. So it's easy to check that the points 0 and 1 are periodic, while the point minus 1 is pre-periodic. So a good picture to see that is the point 0 is periodic because it returns to itself, and point minus 1 is pre-periodic because it comes before a periodic point, which in our case is 1. So this completely defines the pre-periodic structure of the function fz equals z squared. And this is called the portrait of a particular dynamical system. So then let's talk about the projective linear group. It's essentially the set of 2 by 2 invertible matrices up to scalar multiplication. And to each element of PGL2, we can have an identification where a particular, say, variable z, we just have az plus b, cz plus d, where a, b, c, d are just the entries for the matrix. So we can define an action of this set of matrices on the RAD-D space that we constructed via conjugation, which is essentially taking the composition that you see there, where we have alpha compose F compose alpha inverse. And the reason this is so important is because the conjugation that we do on a particular dynamical system preserves the dynamical behavior. So in other words, what this means is that looking at different conjugates, you can get the same dynamical behavior. So it suffices to look at any one of the conjugates of a particular dynamical system. So if you have a certain element of PGL2 where conjugation actually gives you the same dynamical system back, then that particular alpha is called an automorphism of that particular dynamical system. And the set of the automorphisms of a particular dynamical system is the automorphism group, as one would expect. And we have a proposition from PSP in 2009 which stated that the automorphism group of F is always going to be a finite subgroup of PGL2. Now another theorem says that the only finite subgroups of PGL2 are the cyclic group in n elements, the dihedral group in 2n elements, the alternating group in 4 elements, S4 and A5. So we construct an equivalence relation on RAD-D by basically taking a particular dynamical system and looking at the conjugates of that dynamical system and putting them together in the same equivalence class. And this basically motivates the definition for the space that we're actually going to be working in, which is moduli space in dimension in degree D, which is basically taking RAD-D and quotienting out by this equivalence relationship. Remember I told you that essentially conjugation preserves dynamical behavior, so this is why we just look at equivalence classes instead of looking at the space of all maps. Yeah.
For the G to the alpha, doesn't the degree go up when you do G to the... Oh, G, oh, that means something else, sorry.
Yeah,
I just missed it, it's just conjugation.
Yeah.
Got it.
So,
sorry.
no, that's totally fine. So again, you have the fact that if F and G are in the same equivalence class, since because their dynamical properties are preserved, one of the things that also happens is that they essentially have the same automorphism group. They're going to be isomorphic automorphism groups. So, so consider we fix a particular subgroup of PGL2 and call it gamma, and we have the quotient map which takes a particular element in RAD-D and sends it down to MD. Then we define A of gamma to be those maps in RAD-D whose automorphism group contains this particular fixed subgroup as a subgroup. So the space we're at, and the object of our study is essentially going to be this A of gamma, but projected down to moduli space, which is basically what the curly A of gamma is. And that's what we define as the automorphism locus in MD of a particular fixed subgroup of PGL2. And our project was essentially studying what the structure of these automorphism loci look like in these different degree D moduli spaces. An important fact before we go ahead is that if you have G to be a subgroup of H, you can easily work out that you have that the automorphism locus of the bigger group actually sits inside the automorphism locus of a smaller group. And this actually helped us study some of the automorphism loci of bigger groups, which are normally harder to compute, but because we have this information that it sits inside something that we understand better, it helps us understand the other one, the bigger one, completely as well.
Okay, hey, I'm Brandon. So it's sort of useless to do any of these calculations if, like your calculations, right, we need to do everything explicitly. So thank God we have Joe Silverman, right, because he basically did like 95% of the subject is like one of the founding fathers, if arithmetic dynamics had a Bill of Rights, or something like this. Right? So if you just take some function, or some equivalence class of functions, it doesn't really matter, in the moduli space, and you consider its automorphism group. So the reason, first of all, that we consider containment is because equality of the automorphism groups is like ridiculously hard, right? We're just babies for now. So we consider like this inclusion for the easiest case, which is just a cyclic group. And so you conclude that if you have some rational function f, who is an automorphism group, contains a cyclic group, then it has to have the form z times psi of z to the n, where psi is some other rational map. So we have sort of an explicit form for f, right? Like there's, for low degrees, this is effectively computable because there are only so many ways you can write like a degree 3 rational function as a function of z to the n, or for example like z squared or z cubed. So you can just write all these things down right here. And then for the dihedral group, there's like another condition which I didn't put here because we didn't use it a single time, and moreover it would have been troublesome for me to typeset. So I figure if we only use the cyclic group one anyway, then who cares about the other one? And so, like this RAD-D, sort of like you write it down. You see it's a quotient of polynomials, right? So they're So generically, 2 degree D polynomials are not going to share any common factors. So this one up here has d plus 1 coefficients. This one down here has d plus 1 coefficients. So you have like 2d plus 2 parameters, but you note that you can always scale one of them out. So really RAD-D is this 2d plus 1 dimensional space. In particular, it's an affine variety over Q. Which, if you don't know what a variety is, just think you take some polynomials and you take the common zeros. You can just think curve, because that's all we really need. That's what I think when I think of a variety. And So this quotient by, like this PGL2 action, we're quotienting by the action. And so this resulting moduli space, it's like a nice quotient in the language of GIT, it's a geometric quotient. So, PGL2, which is literally just rat1, we know it has dimension 3, so the moduli space is going to have dimension 2D minus 2. So it's a very difficult result that the moduli space is also an affine variety over Q. And it's an affine variety, so it has like some singular points, right? And let's say you want to find the singular locus. So we worked in degrees 3 and 4 because these are computable. And moreover, for degree greater than 2, the singular locus it coincides exactly with the automorphism locus that we defined before. So you figure if you want to understand this geometric structure of the singular points, you can just approach it from its automorphism locus perspective, which is much easier because we have SAGE, right, which will literally just compute these automorphism groups. And so you first have to see like which ones even show up in the for functions in the moduli space, because you can't just like say I want a function which contains A4. Well, that's too bad, right? Because you don't always have that. In particular, this paper by Myasnikov, Stout, and Williams is like the backbone for like this entire part. Because without these results, we would just sort of be left stranded. Because this uses like some relatively difficult machinery to conclude these results. But the main point is that you have like extremely explicit conditions on when automorphism groups even show up for functions in the moduli space. And moreover, like this RAD-D, this MD, they're varieties. And so like the singular locus is a subvariety. And if it's isomorphic to the automorphism locus, then the automorphism locus is a subvariety. And moreover, it has some components, each of which is some family whose automorphism group contains some of these groups. And this time, again, you would expect the dihedral group condition to suck too, but we used it. So I didn't write it down either, just because there's not enough space on the slide. I try to keep this compact, generally speaking. And so what we ended up showing was for each of these families. So not only, this table is sort of appearing out of nowhere, but I will explain it. So for each automorphism group, we found the dimension of the subvariety of MD that it cuts out. And so this is just in dimension 3. So in particular, you wouldn't expect dimension 4, right? That would be kind of strange. So notably, we didn't see any like full dimension subvarieties, which is nice, right? Because that would sort of tell you that you have like some dense set of full dimension whose automorphism group contains like just a given it's just weird, right? It's just not behavior you would expect. And for example, for C2, which is the just cyclic group on 2 elements, right? So this had 2 components, which you wouldn't necessarily expect, but you kind of play around with these coefficients, with these normal forms, and you find that it has 2 components. This fact before, where there's like this order reversing inclusion for subgroups and their automorphism groups. This is what gives you the result for the maximum order of the dihedral group. Because we know a cyclic group is a subgroup. Cyclic group of maximal order is always going to be a point here. And we know that the dihedral group is going to show up. And so we know that it can't be more than a point. And so we just get it for free. And so this table took us about 3 weeks of figuring things out, computations, and it sort of also depends on like the representations of these groups, right? Like for example, to find this normal form for A4, you have to use some special representation because something with a determinant, which if it's not in SL2R, then or SL2C or something, whatever it is, you get some nasty behavior where things might not necessarily be rational. And yeah, we have the same result for M4. So the previous slide took us 3 weeks. This took us 3 days, just because we already knew what to do at that point. And what you notice is that there are no like 2-component families here, which is pretty cool. And again, you sort of have the same thing with the cyclic group and the dihedral group always showing up. One cool fact is that this behavior with the maximal order cyclic group sort of is recurrent in that what's it called? is that in MD, you'll always see the cyclic group of D plus 1 elements show up. And in fact, you'll always see the cyclic group of 2D plus 2 elements show up. And what this is sort of telling you, the notation here is mixed up. This should actually be D10, not D5. But I mean, it's okay, right? Everybody knows what's going on, I hope. So what this gives you is that, like, because we have this explicit list of all the subgroups that can show up in the moduli space, then just writing them down, like generically A5 is, has 60 elements. It's going to be the biggest one. But the next biggest one is going to be this maximal order dihedral group. And so you get an immediate bound on the size of the automorphism groups that can show up, which is just going to be the maximum of either 60 or 2D plus 2. And this is some proposition from like 10 years ago that at first it's like kind of weird, like, wow, that's a cool bound, but it's actually super easy. So this rational pre-periodic structure, thank God we have this board because the pictures I'm about to draw aren't in the slides. So you take like a given rational function. We're just going to restrict to a coefficient being over the rationals, but you can say this for any number field, which are just finite extensions of the rationals. So you want to somehow put a bound on the number of pre-periodic points that it has. And so as a special case, this puts a bound on the number of periodic points. And you somehow want this bound to only depend on the degree of the rational function and nothing else. So as it turns out, this is like a very hard problem. Check this out. Right? It hasn't even been solved for degree 2 polynomials, which you might not expect, right? Because they're all conjugate to something of the form z squared plus c. Like conjecturally, the bound is 9. That's due to Bjorn Poonen, who's like an hour away if you take the train. But it's really hard, right? Because the problem sort of comes down to showing that these cycles, right? So like a fixed point, right? Some x, right? This is a 1 cycle, right? But we can have some more behavior, right? We can have a 2 cycle. You can have an n cycle, believe it or not. And so you sort of, like, the hardest part about this question is just showing that n cycles don't show up for n large. And for degree 2 polynomials, degree 4 was a big result, degree 5 was an even bigger result. Degree 6 uses a weak version of the Birch-Swinnerton-Dyer conjecture. So even for like, or not degree 6, but like these 6 cycles, it's only like conjecturally solved. And so who are we to approach something similar? Well, we're undergraduate students. And so, it's the arrow, sorry. And so we figured that these functions we have, they have non-trivial automorphisms, which if you put, the space of functions is a variety. If you give it a Zariski topology, then it's like sort of easy to be dense in the Zariski topology. But you can show that there's like this Zariski open dense subset of functions which don't have non-trivial automorphisms. And so we figure, well, we do, right? In fact, those are the only functions we're looking at. So let's see if they're easy, right? And so for the n cycles, again, for us that was a hard part too, is showing that they don't exist. But there are like these certain polynomials which encode the information of n cycles, and the fact that we have automorphisms sort of allows you to simplify these polynomials whose degree grows exponentially. And so that's sort of where the usefulness of having non-trivial automorphisms comes in. But really, this basically came down to rational points on curves. And so Brendan Hassett is a professor at Brown University. He's deeply entrenched in these rationality questions. So one question, for example, and here's an reason. This is, I do this face to make everyone relax before the talk. So for this family, right, we have z cubed plus a over az squared. And so over az cubed. I think maybe that should be a square, but let's just pretend it's cubed. You can immediately see that, like, if I plug in 0, right, for z, or a here is just some rational non-zero number, right? If it's not 0, then it's not going to be a morphism of p1, so just, whatever. So if I plug in z equals 0, right, let's just have 0, then it's just going to go to infinity, right? So regardless of what a is, I have like some beginning pre-periodic structure, right? And so we can ask questions. We can ask, does this have fixed points? And so you end up solving for which rational values of a and z. So again, these things are like, this pre-periodic structure is now going to be dependent on this parameter A. So you can say, like, do I have fixed points? Well, let's solve this equation, right? We can, work with polynomials. We can find rational points on curves. So now, okay, let's pretend I have a fixed point. I don't care what it is. Let's call it Z. Or let's call it, not Z, let's call it W, right? So what are some other things I could have? Maybe I could have pre-periodic points of W, right? Well, as it turns out, you can't. Maybe I can have pre-periodic, or points that map into 0, right? So this you can have. You can't have anything else that maps into infinity, right? It's just going to be 0. And so then the question is, well, I can have a pre-image of 0, I can have a pre-image of, or I can have another fixed point. So can I have both? And now you have these conditions on parameters. You see, are there values of both parameters which coincide? The answer is no. So as it turns out, you can have a fixed point, or you can have a pre-image of 0, and you cannot have any pre-images of the fixed point, right? So it just devolves into casework. Right, now the cool thing is that, let's just say I have a pre-image of 0, which I'm also going to call W, right? I'm being abusive here. Now can I have a pre-image of W? So this is sort of where we actually started doing like some arithmetic geometry, because now the rational points on curves question becomes highly non-trivial. The curve you run into, I'm like personally invested into this, is this curve, z cubed plus z squared t to the 4th plus t cubed equals 0, right? So t is just some rational parameter here. And so the question you ask is, are there rational points in z and t on this curve? So you might find an obvious one, which is just 0, right? But 0 doesn't work because that would correspond to this a being 0 down here. So okay, let's look at non-zero stuff. One thing you might notice is that this is degree 3, this is degree 6, and this is degree 3. So my map sending z and t to z omega and t omega, where omega is some cube root of unity. This isn't, I can like do like a true quotient by this thing. But that's not good, because that quotient actually gives us a curve which is birational to P1. Actually, it's not even birational, it's isomorphic to P1. And that sucks because we know this curve has genus 3, so it has to have a finite number of rational points, but P1 is going to have an infinite number of them. And lifting is going to be super annoying and hard, so we use this machinery in arithmetic geometry called the Ash-Mot algorithm, which takes curves whose rank, which whatever the rank is, or the rank of their Jacobian really, is less than strictly less than the genus, and it tells you like, you can get some upper bounds on the number of rational points. Coleman refined this in 1985 to, if you satisfy this rank less than genus condition, am I running low on time? Then you construct some funky p-adic cohomology basically. But what ends up happening is you have this like p-adic integral, and because you have this rank strictly less than genus condition, this gives you existence of some holomorphic 1 form. And at this point I'm talking about nonsense, so you can feel free to tune out. You have like a holomorphic 1 form which annihilates this p-adic integral, and this gives you like some set of zeros, right? So these zeros are p-adic points, and they're going to contain the set of rational points on the original curve, and this gives you like an explicit bound of the number of rational points on your original curve. And sort of the way you do this is you take some reduction over fp, where you want the curve to be smooth over fp. And for small primes, it's like pretty easily, you can calculate it pretty easily. And Magma can do this, but it can only do it for superelliptic curves, which have the form y to the n equals some polynomial in x. And so if you shower frequently like I do, eventually you'll have this like fantastic idea without which I don't know how far I would have gotten with this thing. But as it turns out, this curve is birational to y to the 4th equals x, or oops, y cubed equals x to the 4th plus x. Now in particular, this is a Picard curve. Andrew Sutherland and Jennifer Balakrishnan and her student, I forgot her name, but she helped me a lot. I feel bad now. God, I don't know what her name is. But they have like databases of these curves and their properties, and There's LMFDB, which has data, it's just this giant database of this curve. So as it turns out, this curve has 3 rational points. And so if you do some mumbo jumbo, you go backwards. This curve has 3 rational points. But this is in projective space, right? And so some of the rational points are at infinity. And as it turns out, 2 of the rational points here are at infinity. And so the remaining one is at the origin. And our curves and our functions, these are all over affine space. And so we know that at this point, this has no rational points outside of the origin. And so what's the point of doing all this? I am not very good at using the board, so I erased the pre-periodic diagram. So there's W, which is a pre-image of 0, which is a pre-image of infinity. And this is basically telling us, no, we can't have a pre-image of W. And once you solve this, this is like the whole pre-periodic points done. You say, because you get tired of working with n cycles, that they don't exist for n greater than or equal to 2. And all of a sudden you have a full classification of the pre-periodic structure of this single family, which seems like a lot of work just for this one stupid rational function. But we actually got lucky because this is much less work than professional mathematicians do. Moreover, we did this for another function, which is basically only possible because it had a single parameter. I tried looking at some of these like 2-parameter rational functions, disgusting, right? Like rational points on surfaces is just like, what the hell is going on, basically. And so we have these 2 conjectures for these 2 families, and in theory, you know, if your function is nice enough and if you're clever enough and you take enough showers like I do, you'll be able to sort of do this enumeration of rational pre-periodic structures for basically all of these, right? Like the number of parameters is just a computational hurdle. If you stare at it long enough and if you have enough notepads, you can just write everything down. But this is sort of, I know I kind of started rambling for a little bit, but this is like all of our business with this like rational pre-periodic classification. So, thank you.
So any questions for the speakers?
Yes.
What was the importance of that curve again?
This one?
So like the, yeah.
So rational points on here correspond to rational values of this parameter t, which would for which there would be a pre-image of W here. And so, because the only rational point in affine space here, even in projective space, is just 1, 0, 0, right? So whatever. It's just zeros. And so, because of this, then the denominator in the function is like az cubed. So t here is just some special value of a, right? I just have to keep renaming these things. So because we know that t, like a can only be 0 because t can only be 0, then we're just going to be dividing by 0. Like this is not even a true rational function because these things, because like this radically, it's really like you can canonically identify it with a set of morphisms from P1 to itself, and once you divide by 0, it stops being a morphism. So that's it. Yeah.
Okay.
Yeah.
Wait, so this was finding the rational periodic structure for the specific family of curves, right?
Yeah.
Right.
Well, family of function.
Family of function, and that family was one of the ones in your classification.
Yeah, I mean there were like how many goddamn families, right? Like I'm not gonna do it for all of them. Yeah.
Wait, could you repeat the process for all of them and find the whole?
Sure, if you had more than like 8 weeks. Yeah. Yeah.
I was curious, did you guys look at the Julia sets of these things, and can you look and see the no cycles thing just by looking at the picture? Or is it delicate? Like
It's broken in Sage, isn't it?
I'm sorry? Oh, I don't know. I mean,
Yeah, so a part of our summer project was also building arithmetic dynamic functions in Sage and like repairing some of them. It turns out the Julia function is really badly broken. So we tried to do some of it, but we couldn't really we spent a couple of weeks trying to actually repair that function.
Oh,
but
you mean the
it doesn't
program
work.
just wasn't working?
Yeah, the Julia
I
set
see.
function on Sage doesn't work actually.
yeah, Sage is open source, right?
Yeah,
Yeah.
so that's the problem. But I'm sure something cool could come up if we could.
I mean,
use
you
that,
could also
yeah.
probably have just looked at it by hand, but like, I'm much more inclined towards number theory than I am
Oh,
dynamics.
okay, I was just curious if you could sort of see these things.
Yeah.
Okay.
Any other questions? Last call. All right, let's thank the speakers.
Thank you so much.